All right, now let's take a look at this example 6. I want to determine the intervals of continuity. Determine the intervals of continuity. All right, and here is my function. F of x is equal to this piecewise function of x squared plus 1 if x is less than or equal to 0, and 3x plus 5 if x is greater than 0. Now here's the deal. This is a piecewise, right? So we know that's going on. I know just for the top one, this x squared minus 1, that is continuous. By itself, that's continuous no matter where I am because it's a polynomial. The bottom, also continuous no matter where I am because it is a line. So each piece right now is continuous of this function. The question is, what's happening at 0? What's happening at 0? That's the question, right? I know both of these are continuous and I can plug 0 in and get an actual value here, so we're good there. 0 doesn't get plugged in here because it's greater than. But do these two match up or not? And how do you figure that out? Exactly, with your limits. Do the left limit and the right limit, are they the same? Right? Continuity at a point. What's happening at 0? Step 1, I have a value. Nailed it, right? I have a value. Step 2, do I have a limit? And then are those two things equal? So with a piecewise function, which we learned previously, in order to get a limit, you have to take a limit from the left and the right. The limit as x approaches 0 from the left, right? So that's going to be the smaller than value. That's where I'm going at x squared plus 1 because I'm coming in from the left. Plug it in. So 0 squared plus 1 equals 1. So my limit from the left is 1. What happens when I take my limit as x approaches 0 from the right? That's from the bottom piece. And that's going to be, again, 0 plus 5. So then that will be 5. Now here's my question. Are those equal? No. Is my function continuous? No. Not continuous at where x is equal to 0. So if I want to determine the levels or the intervals of continuity, I'm going to go from negative infinity up to 0 with a parenthesis that I'm looking at because I'm just looking at my intervals here of continuity. So everything, but it cannot equal 0. So, oh, wait. The top, see, slow and steady wins the race. So you guys screaming at me? If you are, good job. This is an or equal to sign. So this up to 0 actually has a bracket because 0 is included in that one, all right? And the intervals, so I'm just listing out the intervals, but then 0 to infinity because this is just greater than. So up to 0 counts and then 0 to infinity. Does that make sense? Because this is or equal to, then my interval is up to 0, that's continuous, but not continuous at 0. Now here's our graph to prove it. Right? Continuous this whole way, including 0. Then I pick it back up again and go on, but not including 0 with that circle. Okay, good. So it's continuous everywhere except at that 0. All right, good job. I can look at lots of other functions if I want to determine continuity. This section wavers back and forth between is this continuous and finding the limit, so make sure you're reading the directions. What values of x make this continuous? That's the question here. So here's part A. G of x is equal to the square root of 9 minus x squared. Now, if you think back to your algebra days, right? When the x squared is in the, oh my, I meant to do the pointer. When the x squared is in the back, right, then that's not infinite. So if you remember that, I know that when my x squared is in my back, I'm going to say, okay, what value's here? 9 minus x squared has to be greater than or equal to 0. And when you factor that, oops, well, you get 9 minus x squared equals 0, and you could even use a square root property. So if you add an x squared to both sides, and then you square root that, then you have, anytime you physically make the square root symbol, you have plus or minus. So x is equal to positive or negative 3. And look what happens whenever I plug the 3 in to the back of it. That gets me my 0. Here, I'm at negative 3 and positive 3, right? But if I were to plug a 0 in, because that's right here in the middle, if I plug the 0 in, the square root of 9 is 3. I know it comes up here. Just stays in between. Do you remember that? So if you don't remember that, or if you didn't know that, now you do, right? That's part of learning. We just learn new things as we come along. So here I have 9 minus x squared. Anytime this squared's in the back, then it stays to the middle. It looks like a little half circle. If the x squared was in the front, that's when it shoots off to the outsides, right? Okay. But with the x squared in the back, that's how I know. And also this minus for my parabola, you know the parabola is going to go down, right? Okay. All those things that you know, you are now expected to take all that prerequisite information and shove it all together and be able to move forward with it. So however you piece that together, it's all that number sense moving forward. All right, so what values of x are going to make this continuous, because we know what this graph looks like in order to pull this off? Yeah, from negative 3 to 3. And they both count because you can have the square root of 0, right? That's valid. So for these kinds of problems, looking at my continuity, just in generic form, if I'm looking at my continuity, then I know that it's from negative 3 to 3. I do not have to take a limit unless there's some type of a question, like in a piecewise or a rational or something that we're trying to figure out, right? But for something like this, I don't have to worry about that. Okay, check this one out. What if I have f of x is equal to x squared minus 2x plus 4 to the 2/3 power? Now tell me things that you know about this. Think about them. Yep, the inside is fully continuous because that's a polynomial, right? What does this 2/3 mean? Yes, it's squared with a cube root. You could actually write this as the cube root here of x squared minus 2x plus 4 squared, right? That's just another way to write that. Well, what do you know is happening with an odd root? Do I have stipulations? No, that's a free-for-all, right? Previous information into the current lesson. So part of what's happening here is just saying, do you recognize a general idea of these functions? And that's what I've harped on up to this point, right? So because this is an odd root, I'm going to scoot it up a little. My handwriting is just super extra bad today. Hang in there, guys. Because this is an odd root, the function is continuous for all x, right? Because it's an odd root, I don't have any issues that go with that. It's continuous for everything. Okay. So continuity of a root, that was what we were talking about here. Even root, you got to play with that a little bit. An odd root is a free-for-all. That's all x's are included because I don't have to worry about that negative under a radical stipulation. Even roots, then you have to think about that a little bit more. And that affects continuity. Okay, go to the next page. What if I have trig functions? Because you know we're going to talk trig, right? What is their domain? What do you already know? You already know for trig that sine, and cosine have all values, right? We already know that. When you have tangent, cotangent, cosecant, and secant, they have asymptotes. So if I'm talking about trig continuity, I should have written that. I did not, because this is about continuity, right? But if I'm talking about trig continuity, then what you know about the actual functions themselves are going to help with some of that. So you think about that with their trig continuity. Bam, that's it. That's all there is to it. What you already know about trig, and then you know about their continuity. What if I want to take limits of trig functions? What if I want this one, example 8? The limit as x approaches 0 of cosine squared x minus 1 over the cosine of x minus 1. Now, what do you always do no matter what? Plug it in. Good job. So if I plug this in, the cosine of 0 is 1. That's an issue. So what else can you do? As soon as you come upon an issue, 0 over 0, then you have to think, okay, well, how can I manipulate this? Yeah, just factor the top. Good job. So the limit as x approaches 0, I have the cosine of x plus 1 and the cosine of x minus 1 over the cosine of x minus 1. I am not talking about continuity here. I'm just finding a limit. This chapter wavers back and forth between both, so you have to pay attention of what you're being asked. In this instance, I'm just asking for the limit. So when I take the limit as x approaches 0 of cosine of x plus 1, you get 2. Because the cosine of 0 is 1, and then you get 2. Okay? Now, here's another little thing for you. We haven't talked about exactly why this is true, and you won't talk about why this is true until chapter 4. However, I'm going to give this to you, and you need to know this one. A common trig limit is the limit as x approaches 0 of the sine of x over x equals 1. All right? It's not obvious without doing work that we're going to cover in the rest of this chapter. In the rest of this course. So just stick with me for right now. Just know this and love this. Once we do L'Hôpital in chapter 4, I'm going to prove to you why this is true. However, your book has you use this now, even though we haven't proven it yet, but it's just one of those things that, okay, just hang with me. I promise to you I will prove it when we get into using L'Hôpital with our, L'Hôpital with our limits. But for now, as x approaches 0 of the sine of x over x, that is 1. All right, that's going to be 1. Okay. Otherwise, you guys have totally rocked the socks off of this. You can do this. Just keep in mind, pay attention. Am I asking for the limit or am I asking for the continuity? And then you got this. Okay, go forth and